Hello everyone, welcome back to Labtube. In this video I'm going to do question 8 from section 16.7. The question asks to evaluate the surface integral of the function x squared plus y squared over the surface which is given by this vector equation, or its parameterization is this, over the region u squared plus v squared less than equal to 1. Okay. Well, first, let's see what you need for this question. The only thing you need, actually I'm going to just write 1 point. What you need is that to know when you have a surface integral and the surface is given by a function like this, then you change your surface integral to double integral by doing these 3 steps. First, write the region for your parameters, u and v. Then, plug in your parameters into your function, the integrand. Then, for ds, you have to compute partial derivative of your vector function with respect to u, partial derivative with respect to v, cross product them, you'll get a vector and find its length. Then du dv. Okay? So if your surface is given by that, those are the steps you have to apply to make your integral, surface integral, to a double integral. When you have double integral, then you know what to do. The next step is make it iterated integral, integrate the inner one, integrate the outer one, and so on. Okay, now let's do this for our case. Our uv is given by this. I have to find our u, partial derivative of the vector function with respect to u. The first component is 2uv. Its partial derivative with respect to u is 2v. Partial derivative of second component is 2u and 2u. There. Our v on the other hand is 2u negative 2v and 2v. And then cross product them. So our u cross our v. Okay, I'm not going to write that, so I'm just doing the cross product because I have it here. So the first component is going to be 4uv minus 2uv times 2u times negative 2uv, so it is plus 4uv. That's the first component. Second component is 4u squared minus 4v squared. That's the second component. And the third component is minus 4v squared minus 4u squared. Okay. Yes, now I can find the length of our u cross our v. First component is 8uv, so it is 8. Let me, yes, okay, 8uv squared plus 4u squared minus 4v squared. I factor out 4, then I have u squared minus v squared. Then the whole thing is squared, the second component is squared. And I'll do the same thing for the next one. I factor out negative 4, but since I'm doing the square root, it's not going to change anything if I put plus u plus 4. Okay. Okay, that's good. Now let's just do open these terms. If I open up this guy, I'm going to get, as you can see, I can factor out 4 actually, 4 squared. So let me put out 4 squared here. Then the remaining is 4uv. 4uv plus, 4u squared v squared. Then the next one is u squared minus 2u squared v squared. This is u squared, this is u to the power 4 minus 2u squared v squared plus v squared, which is v4 plus v to the power 4 plus 2u to the power 2 v to the power 2 plus u to the power 4. And everything is multiplied by 4 squared. Now I can, these two cancel each other, and I have, okay, I have here 4 squared. This is u squared. I have 2u squared, so 2u squared, 2u to the power 4, it's 2u to the power 4, plus 4u squared v squared plus 2v to the power 4. Okay? Now I can easily see if I factor out 2, I'm going to get 4 squared times 2. The remaining would be u squared plus v squared squared. Okay? And 4 squared, if I bring it out of the square root, is going to be 4 root 2 u squared plus v squared. So that's the part for this guy. So RU cross RV is equal to 4 root 2u squared plus v squared. So am I done with everything? It's kind of, because the only part I needed to compute is this one, then the rest is just plug in everything in that function. Okay, let me see if I need this part. No, I don't need, so I can erase these things, these ones. I need to keep this last one there. Okay, so my surface integral here now. Put boundaries for the parameters. It says u squared plus v squared is less than or equal to 1. So I'm just writing u squared v squared less than or equal to 1. For now, it is double integral. It needs a region, so that's the region. Function is x squared plus y squared. X is this, y is that, so I have 2uv squared plus u squared minus v squared squared. That is my function written in the parameters u and v. And then surface element, which is given by 4 root 2 u squared plus v squared, then du dv. Okay, we can simplify this first, maybe. So d is that disk. Now I have u to the power 4 minus 2u squared, v squared, and v squared. So if I do compute this guy, it is going to be u squared plus v squared to the power 2. This part itself, open this up, and you cancel something there, and then you get that. But I also have this thing here, which is the same thing to the power than 1. I add to its power 3, 4 root 2 du. I'm now in a double integral. Double integral, the region is u squared plus v squared less than or equal to 1. That means I can do the polar coordinate for u and v, and write this thing in terms of r and theta. So in this case, because the region is this, and I know that circular and this region are easier to write in the polar coordinate. So instead of setting x equal to r cosine theta, this time I'm setting u equals to r cosine theta and v equals to r sine theta. And this region in polar coordinate, theta goes from 0 to pi, 2 pi. And r goes the length of, the radius of the disk is 1. So it goes from 0 to 1. U squared plus v squared is equal to r squared. So I have 4 root 2 r squared to the power 3. And du dv, you remember in the polar coordinate, dx dy is r dr d theta. You have the same thing here. Okay, now I have a double integral, an iterated integral, and I can do the inner one first. So the inner one, I have r to the power 6, r to the power 7. All the powers gives me r to the power 7, and its antiderivative is r to the power 8 over 8. The coefficients are 4 root. And then going from 0 to 1, d theta. Plug in 1 there, I have root 2 over 2 minus 0 d theta. And this is root 2 over 2 theta going from 0 to 2 pi, which gives me root 2 over 2 pi minus 0. And it is equal to root 2 times pi. Okay, just a quick wrap up. If you have surface integral, you have to change it to double integral, then to an iterated integral. To change it to double integral, you have to have a parameterization. In this case, it is given. And how do you change it to a double integral is written here. So you change the boundary, you write the boundaries for your parameters here, then plug in parameters in your function, and instead of ds, you write this element, partial derivative of r with respect to u, cross product of partial derivative of r with respect to v, find length, times du dv. We applied all these things, our integral here changed to this integral, or this one, this is double integral. But to evaluate double integral, I have to make it into an iterated integral. In this case, we saw because of the region, which was a disk, it was easier to go to polar coordinate, and we applied the polar coordinate change, and then we got this function, this iterated integral. When you have iterated integral, then from there everything is easy. Do inner one, do outer one, and that is the value for your surface integral. And thank you for watching this video.